sklearn cross-decomposition. Description cross-decomposition methods in scikit-learn aim to extract relationships and common variations between two or more datasets. These methods are particularly useful when the datasets are related but not perfectly aligned. They seek to find a set of common components that capture the shared information, allowing for dimensionality reduction, feature extraction, and better understanding of the underlying relationships. Inputs. Input 1x. This is typically a matrix or array representing the first dataset. Each row represents a sample and each column represents a feature. Input 2y. This is the second dataset, structured similarly to x. It could be another set of features, different measurements, or even target values for supervised learning tasks. Outputs. Output 1x transformed, a new representation of the first dataset, transformed onto the extracted components. Output 2y transformed, a transformed representation of the second dataset, corresponding to the shared variations. Steps. Step 1 Decomposition. The algorithm analyzes the input datasets to find a set of common components. This is often achieved through techniques like singular value decomposition (SVD) or non-negative matrix factorization (NMF). Step 2 Projection. The original datasets are projected onto the extracted components, resulting in lower dimensional representations that highlight the shared information. Metrics. Metric 1 Explained variance ratio. This metric quantifies the proportion of variance in the original datasets that is captured by each component. Higher values indicate that the components are effectively capturing the shared information. Metric 2 Mean Squared Error (MSE) in supervised learning tasks. MSE can be used to assess how well the transformed data predicts the target values. Visualization plots. Visualization plot 1 Scatter plot. A scatter plot of the transformed data points can reveal clusters or patterns in the shared variation. Visualization plot 2 Scree plot. This plot shows the explained variance ratio for each component, allowing you to identify the most informative components in the point of diminishing returns in dimensionality reduction. Fine-tune parameters. Parameter 1 N components. This parameter controls the number of components extracted. Higher values capture more variance but can lead to overfitting. Parameter 2 Regularization parameters. Some methods offer regularization parameters to prevent overfitting or to enforce specific properties on the extracted components. Uncertainty methods. Uncertainty method 1 Bootstrapping. This method involves resampling the data multiple times and performing the cross-decomposition on each resample. The variability in the extracted components can be used to estimate uncertainty. Uncertainty method 2 Cross-validation. By splitting the data into training and testing sets, cross-validation can assess the generalization performance of the model and provide insights into its robustness. Challenges and fixes. Challenge 1 High dimensionality. If the input datasets have a large number of features, the cross-decomposition algorithm may struggle to find meaningful components. Sample use case that resulted in challenge 1 Working with microarray data with thousands of genes. Fixes to challenge 1. Feature selection. Apply dimensionality reduction techniques like PCA or feature selection methods to reduce the number of features before applying cross-decomposition. Regularization. Use regularization techniques to penalize complex models and prevent overfitting. Challenge 2 Data scaling. Different scales in the input datasets can affect the extracted components. Sample use case that resulted in challenge 2 One dataset has features in the range of 0 to 1, while the other has features in the range of 100, 1000. Fixes to challenge 2. Standardization scale the input datasets to have zero mean and unit variance before applying. Cross-decomposition. Feature scaling use other scaling methods, like min-max scaling, to ensure that all features have a similar range.